Right. Hello, everyone. My name is Jake Simon, and today I'm going to be talking about planetesimal formation in turbulent protostellar disks. So this is motivated by one of the themes of this conference, which is that planet formation may, in fact, start much earlier than we thought in the protostellar disk phase, as opposed to the class 2 protoplanetary disk phase. I want to mention here my collaborators. I don't have time to go through all of these, but I want to point out my former graduate student from CU, University of Colorado, Daniel Gohl. The work that I'll be presenting today was led by him. Unfortunately for the field, he has left. He works now for Yelp, but this is some excellent work that I'm proud of him for doing over the past year or so. All right, so the main question that I'm interested in answering in general is, can planet formation, and more specifically, can planetesimal formation occur early at the protostellar stage? From a theoretical physics point of view, right? We now have mounting evidence that this is probably the case based on observational data, but does this jive with our understanding from a theoretical perspective? Just as a brief review, because I'm not sure what other talks are going to be touching on this, planetesimal formation itself has been a big subject of study over the past 15 years or so. And that's mainly because it's very difficult to grow these kilometer to 100 kilometer sized bodies from smaller pebbles just by sticking together. You can get micron size growth or micron-sized particles sticking together to grow up to about centimeter-sized pebbles or so. But beyond that, the pebbles encounter several growth barriers to reach the planetesimal size scales. One of them is called the radial drift barrier, which is that at these scales, pebbles tend to drift into the star much faster than they can grow. But the one I'm going to briefly talk about here, because I find this really cool, is based on laboratory astrophysics experiments where they take a canister of centimeter-sized pebbles and drop it from this large tower to simulate microgravity. And the experiments show that it's very difficult to get millimeter and centimeter-sized particles sticking together. They either fragment or bounce apart, or some combination thereof, as shown in these snapshots. And so that's called the fragmentation bouncing barrier. Now, to get around this, there's something that is called the streaming instability, which is a way to clump these pebbles together without actually sticking. So what I'm showing here in this snapshot is a little excised portion of the disk where this is the radial direction, this is the azimuthal direction, the star is far off to the left here, and this is the overdensity of solids. So gray is sort of uniform density starting out, and then red is more, or towards the red end is more and more dense. And as you've seen in the movie that's been playing here, the filamentary structures that develop, there are filamentary structures that develop, and these are due to something called the streaming instability. Basically, pebbles get into these configurations where they're moving together in these filaments. They're not actually sticking together, but they're moving together in these locally overdense regions. Now, what happens when enough of these pebbles pile up in these regions is that their mutual gravitational attraction can overpower the tidal forces from the sun or from the star, and they become gravitationally bound objects, i.e. planetesimals. And so we can now run a number of these simulations in supercomputers, on supercomputers, and basically determine under what conditions planetesimals form, what their properties are, and that sort of thing. And that's been a large part of my work. And I encourage you to see actually Daniel Carrera's talk. He's my postdoc, and he talks about the formation of these planetesimals in pressure bumps, such as those around HL tau. I'm going to touch upon that a little bit at the end of the talk, but I also want to point out that we think that protostellar disks likely have some degree of turbulence. And whether this is due to the magnetorotational instability, which is a magnetic instability in disks, this is shown by this beautiful movie by Mario Floch, or some other mechanism, self-gravity perhaps, because protostellar disks are thought to be quite massive. They haven't yet accreted a lot of their gas onto the protostar, or vertical shear instability, or some combination of these, or there's actually a number of other instabilities, we think that there's some form of turbulence present in these disks. We don't know what exactly or the extent of or how strong the turbulence is, but we think that there's likely some form of turbulence present. So the question is, how does this turbulence influence planetesimal formation? If planet formation happens early, then we have to contend with this notion of turbulence influencing planetesimal formation, and a lot of the studies to date, though not all, have not addressed this question of how this happens. So you saw a little bit about the methods that you saw a little bit about this method in a few slides ago, but basically our method here is to excise a little co-rotating patch of the disk called a shearing box. We do that because the streaming instability operates on very small scales, and you need a lot of resolution to resolve those scales, and so it's cheaper, or it's more computationally efficient to use a small box and properly resolve those scales. This is all done with the Athena gas dynamics code. And there's a number of things here you can read on your own, but I want to point out that we inject turbulent energy into the box manually, in the sense that we add, through a numerical algorithm, kinetic energy into the box, and that mimics turbulence in the sort of generic sense. And the reason to do that is we really wanted to focus on the scales at which the streaming instability is operating and growing, which is less than a tenth of a scale height. And a lot of the instabilities that I talked about before that generate turbulence, such as the MRI, operate on much larger scales. And so to properly really resolve the smallest scales, we had to mimic the effect of these larger scale instabilities and stir turbulence in a sort of generic fashion. And it also allows us to be kind of agnostic as to the source of the turbulence. Okay, so here's the basic result, which is that planetesimal formation gets harder and harder for more turbulent systems. I don't want to spend too much time on this slide, but one of the main takeaways here is that for alpha greater than 10 to the minus 3, no planetesimals form at all. For less than that, you get easier planetesimal formation. It happens more rapidly for weaker turbulence levels. For lower values of alpha, black is the control group here, in which there was no injected turbulence. So the streaming instability itself does have a very weak alpha 10 to the minus 5, 10 to the minus 4 background level turbulence. The reason why this happens, though, is basically because in the case of, it's basically due to an increased particle scale height. So here is a vertical and radial slice of the disk of our box, and this is the midplane here. You can see in the case without turbulence, the dust here has settled largely to the midplane. There is a little bit of turbulence due to the streaming instability itself, but you can also see that planetesimals have formed here. So the particles have settled enough for the local dust to gas ratio to be increased, enough for the streaming instability to be activated. It's relatively well known that the streaming instability requires a local dust to gas ratio of order unity to really produce the clumping necessary to produce planetesimals. And in the turbulent case, you can see that, we just included the same spatial scale here. The particle scale height goes beyond what we're including here. The simulation domain actually extends quite above and below this to capture the full scale height. But the point is that the turbulence in this case stirs up the particles and prevents the local dust to gas ratio from getting close enough to unity. And this is the most turbulent case here. In the intermediate cases, you get just enough regions where the local dust to gas ratio is around 1 or so, such that the streaming instability can operate and planetesimals can form, but in a less efficient manner. So this is the main plot I wanted to show. And this is actually sort of a prediction plot, because these lines here are not empirical. The only data point that's an empirical point is this point here, which is for our runs, we had a stopping time, a Stokes number 0.3. Stokes number is basically just proportional to particle size. It's how well coupled the particles are to the gas. And so these lines are actually lines of constant z, where z is the ratio of particle surface density to gas surface density, based on this formula. And this comes about basically by the definition of epsilon, which is the local particle density to the local gas density for different alpha turbulence. And so again, the only point that's empirical here is this one, but we're extrapolating and seeing, and we basically say, okay, our data is consistent with this formula in that the point at which no turbulence, or sorry, no planetesimal formation occurs versus planetesimal formation corresponds to an epsilon value of order unity, actually a little bit less, for the alpha 10 to the minus 3.5. So for the same tau, we only explored one tau, we then using this equation, make the statement of what, for a constant value of z, what epsilon value corresponds to the alpha turbulence. And basically, the takeaway of this plot is that for stronger turbulence, for a given tau, for stronger turbulence, you need a higher z value in order to overcome the destructive effects of turbulence. And so what that basically means is that you want particles to perhaps be trapped in some sort of pressure bump, or you want weak turbulence in your protostellar disk in order for planetesimal formation to take place. So that's where the conclusions basically are. Planetesimal formation is difficult for strong turbulence. The critical alpha value is 10 to the minus 3 or so. If early planetesimal formation does occur, then the disks must have weak turbulence, or maybe there's particle concentration in rings, and that seems to be the case. Again, see my postdoc's talk. Future work includes exploring a larger parameter space and perhaps determining conditions present in protostellar disks. Can these rings form without the aid of planets? How strong is the turbulence? So I'm running out of time now, and I'm going to stop, but I encourage you to reach out to me and ask questions. Thank you. Bye.